Benzoic acid is one of the oldest and most commonly used chemical preservatives in the food, pharmaceutical, and cosmetic industries. First derived from gum benzoin, a resin found in certain trees, its antibacterial and antifungal properties have made it a staple additive in consumer products for over a century. However, increasing scrutiny from researchers and health organizations has raised concerns about its safety, especially when used in conjunction with other substances. Chapter 1: What is benzoic acid? Chemical structure and properties. Benzoic acid, 6H5COOH, is a simple aromatic carboxylic acid. It appears as a white, crystalline solid and is slightly soluble in water, but highly soluble in organic solvents like alcohol and ether. The benzene ring provides stability, while the carboxylic acid group gives it its preservative properties. Natural and synthetic sources. While benzoic acid occurs naturally in some fruits, such as cranberries, plums, cinnamon, and cloves, the majority used in commercial products is synthetically produced. Industrial production typically involves the partial oxidation of toluene with oxygen in the presence of a manganese or cobalt catalyst. Forms in products: benzoic acid is commonly used in its salt forms: sodium benzoate, potassium benzoate E212, calcium benzoate E213. These salts are more water-soluble and are widely employed in acidic foods and beverages. Chapter 2: Applications and benefits. 1. Food preservation. Benzoic acid is most effective in acidic foods, pH 4.5. Common food products include soft drinks, e.g. colas, fruit sodas, fruit juices and juice concentrates, pickles and sauerkraut, salad dressings and vinegar-based condiments, jams, jellies and fruit spreads, yogurt and cheese products. 2. Cosmetics and personal care products. In cosmetics, benzoic acid functions as a preservative to prevent bacterial growth and extend shelf life. Found in facial creams, shampoos and conditioners, body lotions, toothpastes, mouthwash. 3. Pharmaceuticals. Benzoic acid is used in topical preparations for fungal skin conditions such as athlete's foot, ringworm, and candidiasis. It is often combined with salicylic acid. Additionally, it appears in cough syrups, antiseptic solutions, and ointments. 4. Industrial uses. Benzoic acid has applications in producing plasticizers, alkyd resins, dyes, and as a corrosion inhibitor. It's an intermediate in the synthesis of various other chemicals. 5. Agriculture. Used in some fungicides and animal feed preservatives. Chapter 3: Health concerns and potential risks. While benzoic acid has been generally regarded as safe in low quantities, concerns increase with higher intake, long-term exposure, or combinations with other substances. 1. Toxicological classifications. Reproductive toxicity. Some animal studies suggest benzoic acid exposure can affect fertility or fetal development. Hepatotoxicity. High doses have been linked to liver inflammation and metabolic disruption. Nephrotoxicity. Can accumulate in kidneys and cause oxidative stress. Neurotoxicity. Evidence suggests it may impair mitochondrial function in neurons. Immunotoxicity. May interfere with immune signaling pathways, though data is still emerging. 2. Benzene formation and cancer risk. Under certain conditions, namely the presence of ascorbic acid, vitamin C, heat, and light, benzoic acid can degrade into benzene. Benzene is a potent carcinogen linked to leukemia, bone marrow suppression, immune system dysfunction. Studies have found benzene levels in some beverages exceeded safety thresholds, prompting reformulations and tighter quality controls. 3. Allergy, intolerance, and sensitivities. People with sensitivities may experience urticaria, hives, eczema, asthma exacerbation, rhinitis, abdominal pain, and diarrhea. 4. Hyperactivity and behavioral impact. Some research, particularly the Southampton study, suggests a potential link between artificial food additives, including sodium benzoate, and increased hyperactivity in children. 5. Gut microbiome disturbance. Emerging research shows benzoic acid might alter the composition and balance of gut flora, potentially leading to dysbiosis and its associated consequences. Chapter 4: Regulatory status around the world. United States GRAS by FDA, with a maximum allowable concentration of 0.1% in food products. Limits for pharmaceuticals and cosmetics determined case by case. European Union approved under Food Additive Code E210. EFSA sets an acceptable daily intake ADI of 5 mg per body weight. Labeling required for concentrations above thresholds. United Kingdom follows EU guidance post-Brexit, with additional public awareness initiatives. Canada, permitted with maximum usage levels outlined in the Canadian Food and Drug Regulations. Asia, Japan and China allow benzoic acid within similar concentration limits, but emphasize labeling and compliance testing. Chapter 5. Public Health Case Studies and Incidents. 1. Benzene in Beverages, 2005 to 2007. The U.S. FDA and independent labs found elevated benzene levels in soft drinks containing both sodium benzoate and vitamin C. Companies including Coca-Cola and PepsiCo faced lawsuits and voluntarily reformulated their products. 2. Allergy reports and consumer complaints. Numerous case reports document allergic responses in individuals, leading to calls for clearer labeling and public education. 3. Hyperactivity study in the UK. The Southampton study funded by the UK Food Standards Agency linked benzoic acid and artificial colors to behavioral changes in children. As a result, the EU required warning labels on certain food products. Number 4. Regulatory audits in Asia. Periodic regulatory audits in Asia have flagged local drinks and condiments with excessive levels of benzoic acid, resulting in product bans and recalls. Chapter 6. Safer Alternatives and Innovations. 1. Natural preservatives. Vinegar, acetic acid, used for pickling and fermentation. Citric acid, common in beverages and baked goods. Rosemary extract, antioxidant and antimicrobial. Niacin and natamycin, bacterial and fungal inhibitors used in cheese and meats. 2. Hurdle technology. Combining multiple mild preservation techniques, pH control, refrigeration, modified atmosphere packaging, reduces reliance on single additives like benzoic acid. 3. Clean label movement. Consumers demand transparency and cleaner ingredient lists, prompting companies to reformulate with recognizable minimal ingredients. 4. High-pressure processing, HPP. HPP kills microbes through high pressure rather than heat or chemicals, preserving freshness without preservatives. Plant-based antimicrobials. Essential oils from thyme, oregano, and clove are under research for use in edible coatings and films. Chapter 7. Metabolism, Pathways, and Elimination. 1. Absorption and distribution. Benzoic acid is rapidly absorbed in the small intestine. It binds to plasma proteins and distributes throughout body tissues. 2. Biotransformation. In the liver, benzoic acid is conjugated with glycine to form hippuric acid, which is less toxic. 3. Excretion. Hippuric acid is excreted via urine. Clearance is efficient in healthy individuals, but compromised in those with liver or kidney dysfunction. 4. Enzyme interaction. Benzoic acid may affect enzymes such as cytochrome P450, influencing drug metabolism. Chapter 8. Industry dependence and economic considerations. 1. Cost-effectiveness. Benzoic acid is inexpensive, widely available, and shelf-stable, making it economically advantageous for manufacturers. 2. Shelf life extension prevents spoilage, thus reducing food waste and enhancing logistical efficiency in global food distribution. 3. Small producers versus corporations. Large companies may reformulate in response to public concern, but small producers often lack resources to switch to safer alternatives. 4. Supply chain challenges. Global regulatory differences complicate uniform product formulation and marketing. Chapter 9. Consumer Awareness and Advocacy. 1. Label literacy. Understanding additive codes, E2110, E213, and chemical names helps consumers make informed choices. 2. Advocacy groups. Organizations like the Environmental Working Group, EWG, and Center for Science in the Public Interest, CSPI, monitor and advocate for safer ingredients. 3. Digital tools. Apps like Yuka, EWG's Healthy Living, and Think Dirty help consumers scan products for harmful additives. 4. Education in schools. Some public health curricula now include modules on food labeling and additive risks to foster early awareness. Conclusion: benzoic acid, though widely used and effective, presents a complex web of benefits and potential harms. It is an excellent preservative in acidic conditions, helping to curb foodborne illness and extend product shelf life. Yet its role in forming benzene, potential toxicity, and allergenicity cannot be overlooked. Science continues to evolve, and with it, our understanding of what is truly safe for long-term human health. Regulatory agencies must remain vigilant, and consumers must be empowered through education and transparency. As we look to a future of sustainable and health-conscious living, benzoic acid may still have a place, but perhaps in limited, well-controlled use, as we simultaneously embrace cleaner, more natural alternatives.